Hi, in this video we're going to be talking about parametric equations and curves. So far in calculus, we've only seen functions of the form y equals f of x or x equals g of y. But not all functions can be represented so nicely. So to do calculus on these sorts of functions, we're going to have to write them as an ordered pair xy, each point on the plane, is equal to x of t, y of t, where x and y depend on some parameter t for some t in the real numbers. Now, parametrized curves, since t ranges, our curve actually has a direction, and that direction is going in the direction of increasing t. So let's take a look at an example of a function that we can't actually represent just as y equals f of x or x equals g of y. And we're going to look at a circle with radius r centered at 0, 0, or the origin. Now, note that we can write this as, if we were to write it as a function of x or y, we would only get half of the circle. So, say we were to write it as y equals f of x. Well, there's two solutions. There's y equals the square root of r squared minus x squared, and that gives us the top half of our circle. We could also write it as y equals negative square root of r squared plus x squared, and that's going to give us the bottom half of our circle. Similarly, if we were to write x as a function of y, we would get the right half for our positive square root and the left half for our negative square root. And just looking at the graph of the circle, we can realize that it doesn't pass the vertical line test, so it can't be a function of x, and it fails the horizontal line test, so it can't be a function of y. So if we want to have any hope of representing this as some sort of function, we are going to have to go and use a different method, and that method is going to be parameterization. So before we get into parameterizing the circle, let's first take a look at things that are already parameterized for us. So suppose we want to sketch this set of points x, y, such that x is parameterized by t and y is also parameterized by t. And t squared plus t is equal to x, and 2t minus 1 is equal to y. So what we can do is we can make a chart, plug in different values of t, and see what x and y are equal to. Now, this is not the most efficient way, but it serves to further our understanding of parameterization. So when t is equal to negative 2, x is going to be 4 minus 2, or 2, and y is going to be 2 times negative 2, which is negative 4 minus 1, so y is negative 5. When t is negative 1, then x is 1 minus 1, or 0, and y is going to be 2 times negative 1, which is negative 2 minus 1, or negative 3. Now when t is 0, x is also 0, and y is negative 1. When t is 1, we get x equal 2 and y equal 1. And when t is 2, x is 4 plus 2, or 6, and y is 4 minus 1, or 3. So now that we have this table, let's go ahead, draw some axes, and sketch this graph. So when x is 2, so 1, 2, y is negative 5. 1, 2, 3, 4, 5. So it's about there. And then we have x equals 0, y equals negative 3, and x 0, y equals negative 1. And when x is 2, y is equal to 1. And when t is 2, x is 3, 4, 5, 6, and y is 1, 2, 3. So it's up here. So if we were to connect all the points here, we get what kind of looks like a parabola. And I drew the arrow prematurely because parametrized curves have direction. So the direction of this is going to be what happens as t increases. So we have that when, x goes from, our point goes from 2, -5 to 0, -3. So it's going in this direction, and then we go around. We could probably pick the point -1/2, and we'd probably get this vertex here. And then we go back up. So the general direction of this is swinging around and then back up and to the right. Now sometimes our parameter might be restricted. So it wasn't last time, but now we have t is between 0 and 2. So now we're just going to look at points between 0 and 2. So let's make the same chart, t, x, and y. Notice that we actually have the same functions as before, and that's no coincidence. We're choosing functions that we already have to see how they change with different situations. So we'll make our chart. We'll say 0, 1, and 2. And if we need extra points, we'll throw them in there just in case we need more clarification on what our chart looks like. So when t is 0, x is 0, y is -1. When t is 1, x is 2, and y is going to be 1. And when t is 2, x is 6, and y is 3. So these correspond to the points 0, -1, and then it moves to 2, 1, and then it moves to 6, 3. So let's make a small graph and plot these points. So x is 0, y is -1, and then x is 2, y is 1, and then at 6 we have 3. So our graph looks like a segment of the parabola moving up and to the right. So we see that we could graph these things by making a chart of values, but that's really not the best way in most cases to look at these functions. So another way is eliminating the parameter. So this is when we have two functions of t, and we can eliminate the t. So this is eliminating the t. And we're eliminating the t to just get y as a function of x or x as a function of y. So the easiest one to work with to eliminate our parameter is going to be this. So what we're going to do is we're going to solve one of the equations for t, and then we're just going to plug it in. And what are we plugging it into? We're plugging it into the other equation. So let's look at y equals 2t plus 1. X equals t squared minus t is kind of rough to deal with, and we would have a plus or minus, so that wouldn't really give us a function of x. But with y equals 2t plus 1, we have a linear term. and we don't have to worry about pluses or minuses when we solve for t. So when we go ahead and solve for t, we get y minus 1 over 2 is equal to t. Now we can just go ahead and take this value of t and plug it into our function x. And we get x is equal to y minus 1 over 2 squared minus y minus 1 over 2. So now let's clean this up and get a nice function of y. So x is going to be equal to 1/4 times y squared minus 2y plus 1 minus 1/2 y minus 1. So we can multiply everything by 4 to get rid of the denominator, and then we'll divide it all back in. So we'll have 4x is equal to y squared minus 2y plus 1 minus 2y plus 2. So 4x is y squared minus 4y plus 3, or x is equal to y squared over 4 minus y plus 3/4. Now, looking at our function, we should see that x of y is going to look like a parabola. It should be opening to the right, and its vertex should, well, looking at its vertex, we would have to complete the square. So let's not worry too much about the vertex, but it should be a parabola opening to the right. And if we look back at our graph 2 examples ago, we see here that we do in fact have a parabola opening to the right. Now let's take a look at the locus of points characterized by x equals 3 cosine t and y equals 4 sine t. So this is really hard to eliminate the parameter on. We'd probably have like y equals 4 sine of arc cosine 3 over, or x over 3. While it's possible, that doesn't really tell us much about what it looks like. So let's go ahead and take a look at the table of values. And I did it from negative pi over 4 to 2 pi. You can do it from whatever value you want. I just figured that multiples of pi over 4 are probably the nicest to look at. And if you would like, you can pause the video and double check yours against this. Alright, so what does this look like? Well, if you were to graph all of these points, starting at negative pi over 4, we would start, let's just get this right in the picture here, we would start at about right here. And then we would go to here by pi over 4s along the curve, this in a counterclockwise direction. And when we would hit, so we started here, and when we hit 7 pi over 4, we end up back where we started. And then 2 pi has the same value as 0. So it's this ellipse with height 4 and width 3, and we're going around it in a counterclockwise direction. So let's wrap up the video with our initial question. How can we parameterize the circle? Well, we know that x squared plus y squared is equal to r squared. That is our normal Cartesian way of representing the circle. So now let's divide everything by r squared. So we get x over r squared plus y over r squared equals 1, which is another standard way of writing the circle. Now we're looking at something that gives us, we're looking at something a squared plus b squared equals 1. And what are functions that when I square them and add them together give me 1? And a natural conclusion to that would be sine squared of x, or of theta, plus cosine squared of theta is equal to 1. So if we let sine of theta equal x over r, that tells us that x is equal to r sine of theta, and we can let cosine of theta equal y over r, so y equals r cosine theta. Now if you remember trigonometry, you would see that the sines and cosines are actually flipped, right? They're kind of the opposite of what they should be. But for a parameterization of the circle, this is just fine. So this is not the standard parameterization, but it works. So the locus of points x, y defined by r sine theta, r cosine theta is a parameterization of our circle with parameter not t this time, but instead theta. I hope that this has cleared up some things about parameterization. I will see you next time for another video on parameterization. Thank you for watching.